Hey everybody, welcome back to Young Engineers of Today. How's everybody's weekend? Okay, well I hope you all had a good one. We did something interesting and fun. And I hope you're ready to continue. We are done with 3D modeling, CNC machines, with 3D printing, with all of that stuff. We are moving on to an entirely new topic for the next couple of weeks. And well, you can obviously see on the screen what it's supposed to be. This is going to be all about model rockets. This set of presentations is going to be a few parts. It's going to cover a few different things. Obviously, it's all going to be related to model rockets, but we're probably going to start out with, well, we're going to start out with the very basics of model rockets, basically what they are, what they're composed of, things like that. We're going to spend some time talking about why one might want to use model rockets other than the fact that they're cool. And sort of the ins and outs of flying one and things like that. The different sort of aerodynamics and everything. And then we're going to go over Open Rocket, which is a model rocket simulator. Now, that's not to say that you guys won't be doing anything involving model rockets in lab. Just because we're going to be doing a simulator in the online portion, you guys are going to be making model rockets in lab, more than likely. That's a pretty popular thing that they do most years. So I'd say the odds are very good that you guys are going to end up building model rockets, which should be pretty cool. I think that's always pretty fun. Plus, you'll be able to take it home and put in new engines and launch it and basically just have a grand old time. But yeah, there are a few steps we're going to go through online here. Basically spend as much time as possible learning about rockets. I know, learning. Ugh. And predicting how the launch is going to go before we just end up, building one and launching one and, watching it fly up into the sky and woo. Now, the model rocket simulator, Open Rocket, I should mention, it's probably going to be a little bit drier than you anticipate. That is to say, a little bit less exciting than you anticipate, unless, of course, you find this kind of stuff really cool, in which case you'll probably still find it pretty cool. But, a lot of people tend to imagine something like Kerbal Space Program where you get to watch your rocket fly up in 3D and do all the things. It's generally not the case with Open Rocket. Open Rocket involves graphs and things like that. But we'll learn how to read the graphs. We'll learn what goes on behind it, and hopefully, yeah, well, and explode it. Hopefully you guys will still be able to look at graphs and things like that and go, hey, that's pretty cool. Just because you'll be able to imagine what exactly is going on and why it's doing the things it's going to do. And I know that sounds like such a boring thing to say, but you might be surprised. Allow yourself the opportunity to be surprised. So anyway, like I said, we're going to be starting with the basics of model rockets. So that's going to be just very, very beginnings of stuff. This presentation is a little bit longer than what I have down so far. It's just not all entirely done, I'll be honest with you. So we're going to get through either as much material as we can or all the material that we do have before we break for today, and then we will continue with this topic on Wednesday, and we'll just sort of make progress day by day and learn a little bit more about model rockets each time. So this presentation is essentially, why would we use model rockets? Parts of a model rocket, and we touched very briefly on why we use model rockets, but it's there. And the similarity of model rockets to real rockets. So this is a very light presentation. The next couple of presentations will probably be a lot more in depth on the mechanics of it and the different parts and things like that. But as it stands right now, this is just a pretty light introduction to model rockets. So model rockets, what are they? Well, they're smaller versions of rockets used in spaceflight. Duh. Really and truly, the difference between model rockets and actual rockets is their size and their building materials and the height that they're meant to go. Most model rockets we think of are lightweight model rockets, unless you're thinking of like the really big honking ones. And those are really only meant to go up about 300 feet in the air. They can go higher, but that's usually what they're rated for and stuff like that. If you go higher than that, much higher than that, um, you have to start coordinating with the FAA in order to make sure that you're not launching your rocket into things that are flying overhead. Now, granted, nothing's going to be flying as low as 300 feet, which is why smaller rockets, you don't really care about that kind of stuff. But there are some actual model rockets which sort of toe the line between model rockets and actual rockets. And those you definitely have to coordinate with the FAA to make sure that nobody crashes into it while it's flying through the air. But many of these many model rockets emulate early rocket designs, like very, very early. Like I know this in this picture here, this is a model of a Saturn V rocket, but we're talking earlier than that, like rockets that Goddard made in order to learn about rocketry and things like that. So many of them do emulate very early rocket designs just by virtue of the fact that it's a very simple design and a very easy to make. However, they can be whatever you want if you're patient enough. What I mean by that is you can make something that looks like a Saturn V rocket and launch that thing off. You can make something that looks like a really cool rocket design that you thought, that you think would be a better way to make a rocket or something like that. And you put all sorts of fins and wings on it and stuff like that and try and make some sort of replica of an SSTO, single stage to orbit spacecraft or something like that. And, construct the whole thing and launch it and see how it turns out. Yeah, that could be a thing too. Really, truly, it depends on your patience and your ability to basically make something that's closer to what you envision. And most model rocket kits provide the means to create a very basic rocket, that is to say the early rocket designs. But they can be customized beyond that. 81,000 feet, yeah, see, there you go. 81,000 feet is definitely high enough that you would have to coordinate with the FAA. But yeah. So why model rockets? Question mark. Good job, me. Well, because they're fun. I mean, it is pretty cool to have model rockets and launch them and things like that. Model rockets are enjoyable to build and launch. However, they can be useful to teach the basics of aerodynamics. Yeah, technically. Is it though? I thought it was... I have to think on that. I thought space was higher than that, like the edge of space. Anyway, who knows? I mean, but model rockets can be useful to teach the basics of aerodynamics in rocket design and construction. In fact, they can be very useful for the advanced stuff on aerodynamics and rocket design and construction. It's not exactly a one-to-one sort of comparison because a lot of model rockets are made from cardboard and wood and plastics and things like that. And a lot of go-into space rockets are made of metals, and the propellants they use are much more heavy duty, things like that. But it would be possible, to learn a lot about aerodynamics and rocket design and astrodynamics and things like that. Well, not astrodynamics because that involves being in space, but at least aerodynamics from model rocket design. So the reason they can be used to teach all these things is because model rockets share many similarities with real rockets, actually more than you might think. But, let's take a look at what makes up a model rocket. So on the outside, they're pretty simple. You've got fins, which make sure that it remains pointing upwards and doesn't just wiggle around everywhere. You've got a nose cone, which protects all the stuff on the inside, but, it mainly is meant to sort of pierce through the air, so it increases aerodynamics. You got a body, which is mainly to provide structure and protect the inside of the rocket. I mean, this stuff is all pretty self-explanatory. Now, not shown on the picture here is the set of launch lugs, which are just usually straws or, bits of pipe or something like that. Pieces of plastic that just give something for the rocket to use to hold on to while launching, hold on to like a launch rail or something like that. Well, it's actually lifting off and while it's sitting on the pad waiting to lift off. Because usually model rockets need a little bit of guidance right in the beginning because they need to actually get up to a certain speed in order to be able to fly with any semblance of stability. Any slower than that, and they run the risk of, sort of wiggling about and, not really being stable at all. And faster than that from a dead stop, well, that can, you can run the risk of having too much stress on the body or in the fins and shearing things off. Granted, not really going to happen too much with model rockets, but it is something to worry about, certainly with real rockets, and it's something that translates at least a little bit to model rockets as well. So that's the outside of the model rocket. Not a whole lot to talk about there. It's just got a rocket structure to it, kind of what you'd expect. However, the inside, there's a bit more going on. Thank you, NASA, for this very helpful diagram. So let's go through at least most of this stuff one at a time. So as you can see, you've got the outside of the rocket here showing. You've got the body of the rocket. You've got the nose cone. And the nose cone is generally just a solid thing. There's not really anything going on with the nose cone special. It's just a solid piece of wood or plastic or cork or something like that, meant to just stay on the top and increase the aerodynamics of the rocket. Then we've got the fins here. And actually, these green things here are the launch lugs. So they're just mounted on the side of the rocket, and the rocket is then, the launch lugs are then slotted onto the launch rail in order to provide, the stability that the rocket needs for liftoff. So the first part is the engine, which is obviously what provides the power for our rocket to go up. Go into more detail on sizes and figuring out what's what later on, and basically what makes up a rocket or rocket engine. But model rocket engines are just these self-contained things that are replaceable. You can slot in a new engine once you use the old one. It's very different from, in that sense, from many real-life rockets. Real-life rockets, if they're liquid engine rockets, they'll have, not everything will be self-contained. You'll have basically fuel tanks that you will refill with hydrogen and oxygen, or liquid aluminum mixture. It's an ion of aluminum. It's very strange. Anyway, regardless, they'll have actual sort of fuel tanks for it. Solid rocket boosters are kind of more like solid rocket engines, in the sense that they are, very much integrated. The inside of a solid rocket engine is essentially the fuel. The inside of a solid rocket booster is essentially the fuel as well. However, solid rocket boosters can still be reused. It's not like they're lost necessarily as soon as they're used up once, whereas a solid rocket engine is generally not refillable, at least for smaller model rockets. But they do share similarities. Solid rocket engines on model rockets cannot be turned off. Solid rocket boosters on real-life rockets also cannot be turned off. As soon as the reaction is started, they burn until they're out of fuel. This is very different from a liquid engine. A liquid engine can be turned off. A solid engine cannot. So that's something also to be taken into consideration, by engineers and stuff like that when they're constructing rockets. The engine mount, make sure that the engine doesn't go anywhere. It's generally just a bracket that the engine slots into and a little locking mechanism. And this is useful because if the engine isn't mounted to the body of the rocket, well, you could light the engine and then it would just shoot up through the center of the rocket. Or it could have somehow miraculously stayed in place, and then as soon as it shoots the recovery charge, it could just blow itself out of the bottom of the rocket and not actually, deploy the nose cone or the parachute or anything like that. So, you put the engine mount in there in order to ensure that the engine stays affixed to the same place on the rocket, and all the forces that are exerted by the engine are exerted upon the rocket, thus making it move around and, do generally rockety things like fly upwards in the air. Then you got the recovery wadding, which just provides a bit of protection against the ejection charge of the engine, which we'll, talk more about later. You got the parachute. Parachute makes sure that the rocket doesn't fall to the ground like a rock and break. So, you want to make sure that it's recoverable. That's the parachute. Nothing really crazy there. The shock cord is meant to keep the nose cone attached to the rocket even after it deploys the parachute. So, the nose cone is meant to be just as recoverable as the rest of the rocket. The shock cord, it basically attaches the nose cone to the inside of the rocket body, ensuring that the nose cone doesn't go flying away as soon as the ejection charge deploys. Like, it'll still be dangling from the rocket. And in addition, part of the reason why it's called the shock cord is it's specifically designed to reduce the stress of the nose cone being blown off by the ejection charge. The shock cord is generally some form of elastic cord that has a lot of elasticity to it. If it was like, a solid, like a string or something like that, something that had not a lot of play, there could be enough force when the nose cone is blown off that it could actually rip itself out of the inside of the rocket, or it could damage the inside of the rocket, if the string was actually affixed tightly enough. Just because the amount of force that's involved in blowing the nose cone off and the parachute out and stuff like that is, pretty stressful for paper or cardboard. So the shock cord is specifically designed to hold on to the nose cone while minimizing the amount of force that the rest of the rocket feels by it. This also goes hand in hand with the fact that, assuming none of those things happened, assuming the inside of the rocket wasn't damaged by it, and the nose cone stayed affixed and everything like that, it could potentially like pull the rocket sideways. Shock cable's meant to sort of minimize that as well. Or shock cord, I should say. Parachute lines keep the parachute attached to the rocket. Like I say here, otherwise it dropped like a rock with a bit of parachute gently floating down after it, which would sort of defeat the purpose. You want to make sure that the parachute slows down the rocket. That's kind of an important part of recovering a rocket and having a parachute to do that. And then, yeah, on this diagram you can see launch lugs. So in the end, this is more complicated, more complex than the outside of the rocket, but it's still not too bad. Basically, it's just a recovery system. The engine's mounted on the inside, and then there's an entire recovery system to make sure you can at least get the rocket back. And that's about it. Otherwise, it's not too crazy in here, right? Like, I mean, it makes sense. So in addition to that, let's take a closer look at what's going on inside of the engine, because the engine itself has a few separate parts to it as well. The solid rocket engine. Whoops, extra slide there. Let's get rid of that. Boom. So the actual model rocket engine is made up of a few different parts that all work together in your model rocket. So it's got a few different sort of sections to it that all serve different purposes. Bottom part is the clay nozzle. It's really, there's not much to it. It's just clay, so it's heat resistant and shaped in order to provide directed thrust for your rocket. So you might want to think of thrust vectors on jets and real-life rockets and stuff like that, or the nozzles on rockets. It's simply because if that wasn't there, the propellant would be burning, and it would just sort of all burn in a general downward direction with no actual real focusing or anything like that, and it probably wouldn't provide very much thrust, maybe not even enough thrust for a model rocket to lift off, So the clay nozzle, the entire point of that is to take all of the thrust that the propellant exerts and basically put it into a much smaller radius, which would then make the rocket go upwards. Thank you. So the propellant, as the name implies, is your main source of thrust on the rocket. It makes it go up, burns, and makes a whole bunch of hot gases and stuff like that. It forces those hot gases out through the clay nozzle, and then the hot gases going downwards makes the rocket go upwards, and science happens and the rocket goes flying. So after the propellant, there is a delay charge, and it's labeled delay charge and tracking smoke. it spends some time burning after the propellant is done, so that the rocket can continue to coast upwards before the parachute deploys. Because essentially, I mean, inertia is a thing. Even though the uh, the propellant is no longer burning, the rocket will still be experiencing some upwards inertia because, well, no, Newton knew a thing or two about physics, and basically one of his laws was that a body in motion stays in motion and a body at rest stays at rest unless it is acted upon by an outside force. The same is true here. The rocket, assuming that there was no such thing as gravity or air, like if we did this out in the middle of space, out in the middle of nowhere, the rocket would continue moving in the same direction forever. Same is true here, except we've got gravity and air slowing the rocket down. So we want to just sort of make the most of that before we, end up deploying the parachute. On top of that, if we decide to deploy the parachute while the rocket is still moving very quickly upwards, the air could actually be moving too fast for the parachute to work properly. It could break. It could break the inside of the rocket, something like that. So we also wait until the rocket has actually slowed down a bit in its upward ascent before deploying the parachute, in order to make sure that the parachute properly deploys, can slow down the rocket, and there's a minimum amount of force that is exerted upon the rocket itself. So the delay charge is there just to sort of burn and not really do anything, but take its time burning before we deploy the parachute. In addition, a lot of times these things burn with a smoke, like a colored smoke of some sort, so that you can actually see your rocket more easily once it is flying around up in the air, upwards into the air. So there's that as well. It serves a dual purpose. Then finally, you've got the ejection charge, which burns very quickly, almost instantaneously, in order to create enough pressure to blow off the clay cap that is above it. The clay cap basically goes upwards, and, well, essentially what happens is the ejection charge, the same thing happens there that happens at the propellant. A bunch of the surrounding air is superheated, well, not superheated, but it's heated very quickly, which causes the air to want to expand, because that's what hot air wants to do, is it wants to fill as large a volume as possible. And then it, one moment. Oh, I didn't realize I was muted. Oh, one moment. How long have I been muted? A little bit? Okay. Was it around the time I said I would be back, or one slide? Okay, well, I'll go back. So, did you hear my whole talking about pressure and everything like that? I don't think, yeah, I'm not sure if that whole explanation came through though. Well, in essence, okay, yeah, how the heat fills up space. Okay, so yeah. So it blows the clay cap off. The hot air fills the inside of the rocket, and then that increases the pressure on the inside of the rocket, which forces more hot air to want to go upwards, and so on and so forth. And that's why the recovery wadding exists there. The recovery wadding is meant to be sort of what pushes everything outwards, and the hot air is meant to be behind. Is meant to be. This doesn't all work out in practice exactly perfectly, but then you got the hot air behind it and the regular air in front of it, and the hot air expands and pushes the recovery wadding outwards, which pushes on everything else. The reason you have that is because the recovery wadding is meant to also serve as a barrier against the heat. Depending upon the type of parachute, most of these parachutes are going to be plastic or some form of sort of like wax paper or something like that, or parchment, whatever. Sometimes, if you want to go super fancy, you can go with like a sort of a cloth or something like that. But regardless, these things are sensitive to heat. Parachutes are generally pretty sensitive to heat. You want to make sure that a parachute is lightweight, but also strong and elastic against air and stuff like that in order to slow down whatever it's meant to slow down. This is generally incompatible with a heat-resistant parachute. So for that reason, the recovery wadding is in there in order to protect the parachute from the heat of the ejection charge and the subsequent hot air that follows from it. So because, if the parachute melts and turns into sort of a molten ball of plastic or gets a hole in it or something like that, well, that sort of defeats the purpose of the parachute, and thus your rocket falls and everybody's sad. So, you always want to make sure that your recovery wadding is packed, well enough also. So there's that. And then the clay cap is also just meant to provide some heat protection as well, and also a hard thing to be launched upwards in order to deploy the rest of the rocket, or the recovery system on the rocket. It's nothing crazy, but it all sort of works together in order to generate a functioning rocket. So with all of that put together, a typical launch for a model rocket will likely look something like this. So we'll look at this entire diagram in separate parts. So you'll have your rocket sitting on the launch pad with the launch lugs affixed to the launch rail. The rocket is pointed upwards. It's probably sitting on a small pad in order to provide something to shoot off of at launch time. And then the engines are ignited, usually using a small electrical charge. Like you'll hook some wires up to the motor engine, and then usually the ignition switch is exactly that, something hooked up to a couple of batteries or whatever. You press the button, it causes a small spark to shoot between the two wires that you've hooked up, which is enough to ignite the gunpowder that is inside of the engine. The gunpowder, ignites, starts to burn, creates a reaction. It starts burning fast enough that you get power descent. So the propellant part of the engine provides the upward acceleration for the rocket, making it, do what rockets do, which is go up, ideally. And this continues for usually not very long. I mean, you have like a second or two of actual power descent. It's a very, very rapid stage. It happens very quickly. The rocket gains a lot of altitude in a very short period of time. But you'd think like it would last longer than it actually does. But the actual power descent part is just, and that's it. And then from that part, it's coasting. Propellant runs out, the delay charge begins to burn, and you usually see some sort of darker smoke or something like that there. Or maybe it depends upon the the manufacturer. Sometimes you'll see darker smoke, sometimes you'll see even like lighter smoke. But either way, it's meant to be something so that you can actually see your rocket in the air, because at this point your rocket is higher in the air, which means that it's harder to view, especially depending upon how you've painted it and things like that. So there's some helpful smoke which can come out in order to help identify where your rocket is. In addition, the rocket, as you can see here in the diagram, the rocket's sort of tilting to the side, and then it eventually at some point becomes sideways. This can actually very likely happen, especially if your nose cone is made out of like wood or cork or something like that, because when the rocket is sitting on the launch pad, it tends to be more bottom heavy, or at least evenly weighted. As the rocket gets higher in the air, it becomes more top heavy, because gunpowder weighs not insignificant amounts. So you want to excuse me, as it burns, I'm just all out of sorts today. As it burns, it removes more of the weight from the bottom, transfers it into force that's making the rocket go upwards, and the rocket becomes more and more top-heavy as it gets higher and higher in the air. And then you'll usually see a sort of tilting of the rocket that happens as it's adjusting to that. You know, the fins will provide stability, but they don't, as it enters coasting flight, the air is not moving past the fins generally quickly enough in order to keep the rocket pointed directly upwards. During power descent, sure, especially as the propellant gets low, the rocket is still moving fast enough in order to keep the rocket pointing straight upwards. But as it slows down, the fins can't really do their job as well, so the rocket begins to tip in order to compensate for the fact, especially if it already had a slight leaning to begin with, in order to compensate for the fact that it's now more top-heavy, and then it'll coast for a while. Then the ejection charge is hit. After the delay charge is already burnt out, the ejection charge is hit, and the nose cone pops off, the parachute is deployed. You'll probably see some streamers and stuff pop out depending upon what your ejection charge is, or excuse me, your what's the word I'm looking for? Recovery wadding is. Some people like to put like streamers and things like that for their recovery wadding, so the front of the rocket blows off, and then there's just a bunch of like purple and green papers come like flying out of the rocket, and then the parachute. So it's like a party favor in the air. But yeah, it burns nearly instantly, blowing the nose cone off from the inside. Then the shock cord absorbs much of the force, and the parachute deploys. Hopefully deploys, holding the nose cone and the engine and the body and the fins and everything. And it will slowly sort of drift to the ground, where you can then recover it, pick it up, and prepare it for another launch. Usually this involves another engine, so you just take the engine that's out. Obviously you want to wait for it to cool down, because those engines can get pretty dang hot. So you'll basically replace the engine with a new one and repack the inside with more recovery wadding, and repack the parachute and everything like that, and then put the nose cone back on. Now, one moment. This is not to say that these rockets are infinitely usable, especially because they're built out of cardboard and stuff like that. As they're used, the engines can actually become hot enough to start burning the body of the rocket, and lowering its structural integrity. And if the fins are glued to the wings and stuff like that, enough heat, depending upon the type of glue you use, can actually cause the glue to become liquid again, which is bad when the rocket is flying upwards. A fin might fly off, which won't happen immediately, but over time it can reduce the structural integrity of the fins and stuff like that. And the nose cone, the shock cable on that could potentially fall off after a number of uses, which then can make the nose cone fall, which can break the nose cone potentially depending upon what you're launching over, so on and so forth. In addition, just landing, even though it's got a parachute, it doesn't always slow the descent to a gentle landing. Sometimes it's still a little bit dramatic, just not enough to really guarantee that the rocket's going to break. But if you've launched it a few times, you can still run the risk of the rocket actually breaking upon touchdown, even though you're using a parachute, just because it's happened so many times. So yeah, not 100% reasonable, but decently so. So now hopefully you can kind of get an idea of how all of these things sort of work together in order to create a rocket launch from start to finish. Start being sitting on the launch pad and finish being recovery. Ugh. So this is all well and good, but how does this compare to full-size meant-to-go-to-space rockets? This is actually right now running at the end of the material that I have, so we're going to definitely end it early today. Wednesday will be a longer session, but we'll spend some time, on the next slide, and then we'll call it a day. So let's go back real quick to the inside of this rocket. We've got our recovery system, we've got our propellants, we've got our, well, that's it. We've got our nose cone as well. Our nose cone provides some stability, our fins provide some stability, our launch lugs provide some stability, but all in all, this is a very simple system. Everything is either facilitating recovery, stability, or thrust, and that's it. Everything has a place. Or structure, I suppose, but you can also count that under stability. It's a very unstable rocket that has no structure. Well, looking at an actual rocket, it might be set up a little differently, but you can hopefully see the similarities here. We've got a payload system, a guidance system, propulsion system, which includes fuel, an oxidizer, pumps, and nozzles. The nozzle being the actual part of the rocket that the thrust shoots out of. We've got the structure system, provides stability, nose cone, fin, stability, frame, stability, propulsion system, propulsion. The payload system and the guidance system will be obviously stability in order to ensure that the rocket is flying straight and not off course and things like that. But the payload system will usually contain some means of recovering the rocket as well. So you've got a recovery system right there. So now you can see the ratio of everything is different. Obviously, there is a lot more devoted to the propulsion system, and this is because this is meant to go, to space, and it's larger and it's heavier and so on and so forth. But all in all, it's got the same sort of stuff. The payload system, also the recovery system, is smaller, generally because these rockets, they have, well, again, because they're larger, they can devote a smaller area to, relatively speaking, to the recovery system because parachutes compress down very well. So, the parachute that we have here, since our rocket is so small, a very large area of it is devoted to the parachute. But on top of that, a very large area of the rocket is devoted to recovery system, and there's a lot of inefficiency. We could actually, decrease the amount of area on the inside and still have a competent recovery system. But this also, sort of ensures that everything deploys correctly, and we don't end up with like a fire on the inside or anything like that, and nothing's deployed too quickly. So there's stuff like that. And yes, just in case you're wondering, ironically, you can have your nose cone be too loose on the rocket, and thus let escaping air out too easily, thus making it harder for things to actually deploy. It's not really that common, but it can happen. Sometimes you might worry that the nose cone is on too tightly. Generally, having it on pretty tight is a good thing as well, because that ensures that the pressure buildup is enough that everything gets sort of ejected once the nose cone finally pops off. Anyway, yeah, the ratio of recovery system to the rest of the rocket gets smaller as the rocket gets larger, again, because parachutes compress themselves pretty well. In addition, The air itself does a pretty good job of slowing down a rocket, and they also tend to land in water, which is more forgiving on things. You know, water is still a pretty dense thing to run into. You know, falling into water can still be pretty hard, physically speaking, on things. But all in all, it could be much less rough than landing directly onto solid ground. So for that reason, you know, you don't have to devote as much area to recovery, and you have to devote more to propulsion because you have to go up higher. But regardless, you can see here that the basics all sort of exist. You've got fins and the body and the nose cone. You've got the engine. You've got the recovery system. And that's that. But yeah, we're going to go ahead and we're going to call it a day here. Honestly, because I actually need to create more material for this. Created this as quickly as I could in the time that I had, but you know, obviously there's still a ways to go. But we will definitely have a full class on Wednesday. That is to say, we'll go the entire hour, and we will make good progress on this over the next few weeks. We'll learn a lot about model rockets, how to set them up, how to make them as efficiently as possible, things like that. You know, sort of things like fin design and stuff like that in order to make it as stable and fast as possible, like a good balance between the two. We'll learn about, you know, the engine ratings and things like that in order to understand how they differ from one another, and you know what kind of engine might be the best one for your model rocket. We'll learn about sort of the how to most efficiently pack the parachute and the recovery wadding and things like that. So, you know, there will be a lot that we'll go over in the coming weeks. Hopefully you guys find that interesting. Hopefully you found this interesting, albeit short. But that's what we're going to spend the next few weeks talking about. So with that, I'm going to go ahead and do the poll questions. If you have any questions about anything, I'll be here. I imagine you might have a few, maybe. But otherwise, once we're done with the poll questions, you can head out and have a great couple of days, and we'll see you on Wednesday.